Now we are going to see example number 3, and example number 3 is given by, we have to prove variance of E1 dot 23 is same as covariance between x1 comma E1 dot 23, and which is equal to sigma 1 square minus sigma 1 square dot 23. It is a variance of residual x1 dot 23, and it is variance of x1. So what is E1 dot 23? It is defined as x1 minus x1 dot 23. So expected value of E1 dot 23 is same as expected value of x1 minus expected value of x1 dot 23. As x1 and x1 dot 23 are measured from their mean, x1 is measured from their mean and x1 dot 23 is residual, so both expectations are 0, so it is 0. So variance of E1 dot 23 is 1 upon n summation E1 dot 23 minus expected value of E1 dot 23 bracket square. But we have shown that expected value of E1 dot 23 is 0. So 1 upon n summation is square 1 dot 23. So what is expected value of, which is equal to 1 upon n summation E1 dot 23 is x1 minus x1 dot 23 square. So by using perfect square, we will have x1 square minus 2x1 x1 dot 23 plus x1 dot 23 square. So 1 upon n summation x1 square minus 2 is constant, so take it outside the summation, 2 upon n summation x1 dot 23 plus 1 upon n summation x1 dot 23 x1 dot 23. So what we have, it is a variance of x1 1 upon n summation x1 square, as x1 bar is 0, and this we have to consider what it takes. So by second property of residual, we can write x1 as x1 dot 23 x1 dot 23. Since second order secondary substitute of this residual comes in secondary order secondary substitute of this, so this sum of product remains unaltered if we remove x2 2 3 or both 2 3. So we can write by using second property, plus 1 upon n summation x1 dot 23 x1 dot 23. So it is minus 2 upon n plus 1 upon n, so which is equal to minus 1 upon n summation x square 1 dot 23 sigma 1 square, and as expectation of x1 dot 23 is 0, so it is variance of residual 1 dot 23 as its mean is 0. So we have proved LHS. Now we have to prove covariance, comes out to be this. So to show that, consider covariance between x1 E1 dot 23. So covariance is same as 1 upon n summation x1 minus expected value of x1 into E1 dot 23 minus expected value of E1 dot 23. So 1 upon n summation x1 into E1 dot 23 into E1 dot 23, as expected value of x1 and expected value of E1 dot 23 are 0. So now what we have, 1 upon n summation x1 minus x1 dot 23. So 1 upon n summation x1 square minus 1 upon n summation x1 dot 23. So 1 upon n summation x1 square, by second property of residual we can write x1 as x1 dot 23 x1 dot 23. So what we have, 1 upon n summation x1 square minus 1 upon n summation x square 1 dot 23. As mean of x1 and x1 dot 23 are 0, so these are nothing but variance, sigma 1 square minus sigma square 1.23. So we have proved that this is same as variance of E1.23. So we have proved another example 3. Now we are going to another example. So what is our next example? We have to show variance of x1 greater than or equal to variance of x1 dot 2 is greater than or equal to variance of x1 dot 23. So we have derived variance of x1 dot 23, variance of residual, is equal to sigma 1 square determinant of r divided by r11. This is sigma square 1.23. We have derived this in previous lectures. We have proved this is equal to this. So now we have to consider variance of x1 dot 2. Variance of x1 dot 2, so it is equal to summation 1 upon n summation x1 dot 2 minus expected value of x1 dot 2 bracket square summation x1 dot 2 square. As we know that expectation of residual is 0. Expected value of x1 dot 23 is equal to 0. Similarly, we can show that expected value of x1 dot 23 is also 0 because this is a expectation of residual. 1 upon n summation x1 dot 2 x1 dot 2. We have written just square as product. So 1 upon n summation x1 into x1 dot 2. So by using property of residual, we can return x1 dot 2 as x1 and x1 dot 2. So 1 upon n summation x1 dot 2 is x1 minus b12 into x2. So which is equal to 1 upon n summation x1 square minus b12 take outside since this is constant, 1 upon n summation x1 x2. So what we have, b12 into this, so which is equal to sigma 1 square minus, this is sigma 1 square minus b12 is sigma 1 upon sigma 2 r12 into, this is 1 upon n into sigma 1 sigma 2 r12, and which is equal to sigma 1 square minus sigma 2 gets cancelled, sigma 1 square n gets cancelled, sigma 1 square into r12 square. So we have this equal to variance of x1 dot 2 is equal to sigma 1 square into 1 minus r12 square. So we have this. And variance of x1 is sigma 1 square. So now what we have? We have to show that variance of x1 is greater than this. So we consider variance of x1 minus variance of x1 dot 2. Variance of x1 is sigma 1 square minus sigma 1 square 1 minus r12 square. So what is it? Sigma 1 square take outside, 1 minus 1 plus r12 square. So it is equal to sigma 1 square into r12 square. So both are squares. Sigma 1 square is always positive. R12 may be negative or may be positive because it ranges from -1 to +1. But square of this is positive. So this is positive. This difference is positive. That means variance of x1 is greater than variance of x1 dot 2. So we have proved this. Now we have to prove this. So consider variance of x1 dot 2 minus variance of x1 dot 23. So what is variance of x1 dot 2? Sigma 1 square into 1 minus r12 square and minus sigma 1 square determinant of r divided by r11. So now we have to prove this is a positive. So to do this we take sigma 1 square outside the and r11. So we have r11 into 1 minus r12 square minus determinant of r. Now we will solve this, and what we have, we will see. Sigma 1 square, r11 is r11, deleting first row and first column, we have r11, 1 minus r23 square. So r11 is 1 minus r23 square into 1 minus r12 square, and we know that determinant of r is 1 minus r12 square, r13 square, r23 square plus 2 times r12, r13, r23. Now this as it is, multiplied both brackets, 1 minus r12 square minus r23 square plus r23 square, r12 square. So minus 1 plus r12 square plus r13 square plus r23 square minus 2 times r12, r13, r23. So what we have? This term is as it is in a bracket. This 1 gets cancelled. r12 square, r23 square cancel out. So what we have? r13 square minus 2 times r12, r13, r23 plus r23 square, r12 square. So this term is as it is. Sigma 1 square divided by 1 minus r23 square into bracket, this is a perfect square of r13 minus r23, r12 bracket square. So this square variance is always positive. This whatever it comes negative or positive, because these are ranges from -1 to +1. So square is positive, and 1 minus r23 square is always positive because this is square is less than 1. So this is positive. This positive means variance of x1 dot 2 is greater than variance of